So now we'll try to do an example so you get some sense for what this actually is useful for. So we're going to consider a simple nozzle here. We've got an inlet of the nozzle. It's 8 centimeters in diameter, an outlet that's 2.5 centimeters in diameter. There's an inlet velocity. Obviously, there's an outlet velocity. We're going to consider water. Water is going to enter a nozzle at uniform velocity of 0.5 meters per second. That's 0.5 meters per second. And we're going to try to find the average outlet velocity using our new technique of control volume analysis. Not really new. You could have done this in thermo, but we're treating it as new today. So we're going to consider that, well, is this incompressible? Well, yes, it absolutely is. Water, of course, is incompressible. It's an incompressible substance. So we don't need to worry about that aspect of this problem. Water is definitely incompressible. In fact, we even know the density. It's 1,000 kilograms per meter cubed. So that's good to know. Maybe we'll need that. Maybe we won't. Turns out we won't, but it is. We know it's definitely incompressible. So we're going to make the control volume be the nozzle. So for the, if you want to draw your little dotted line like from thermo, it would be the nozzle here. That's our control volume, and that volume is fixed. So nozzle volume is fixed. So we have the case of a fixed volume incompressible situation, which means we can use this equation as our conservation of mass. So that's what we're going to do to get comfortable with this equation. So that's the equation we're going to use. That is valid for fixed volume incompressible flow. So, all right, so how do we actually, use this? So, well, the first thing to realize is that, on this surface, right, what's u dot n here? So u dot n hat right there on the solid outside of the nozzle, that's 0 because u is 0. So we know from the no slip condition that u is 0. We also know that water is not going in or out of the nozzle through the nozzle sides. That these, imagine they're made of metal. So this is going to be 0. There's no in or out flow here. So the whole integral across that area, anything along these edges, that's all going to be 0. So the only place this integral can be not 0 is both at this surface here, the inlet, and the surface back here, the outlet. That's the only place where u dot n is not going to be 0. Everywhere else, the nozzle is a solid object. U is going to be 0 at the surface of the solid. U dot n is 0 also because aside from the fact u is 0, you know that nothing is entering or leaving through a solid object. So the only place where u dot n is going to be non-zero, that is the only place you have to take this integral, is at the inlet surface and at the outlet surface. So that's important to understand. You don't have to take the integral over surfaces that are just where u dot n is simply equal to 0. So that's just simply equal to 0 there because it's a solid surface. So we don't have to worry about that. So we only need the integral over the inlet and the outlet. Only need to evaluate integral over inlet and outlet where u dot n does not equal 0. So that whole integral can be thought of, from s u dot n ds is equal to a area over the inlet of u dot n in ds and the outlet u dot n ds. So those are the two that we have to actually do because everywhere else this stuff is 0. So over the inlet, we have the inlet, we've got this average velocity coming in. Our outward unit facing normal is going to be that way. It's going to be pointed the other way, opposite to the flow, right? Because the outward unit normal is that way, our nozzle's over here. And so we know that this u dot n at the inlet, that's going to be negative, right? Because that's going to be opposite. They're going to be opposite. That dot product's going to give us a negative sign there. So that's going to give us a negative sign. U dot n is going to be negative. but it's also going to be a value 1. I mean, it's going to be the whole value because they are in actually opposite directions. So the dot product is not going to change the magnitude of u. It's just going to give it a negative sign. So u dot n at the inlet is going to be negative u at the inlet. And we know what u at the inlet is. It's 0.5. So it's negative 0.5 meters per second. So that's u dot n at the inlet. It's going to be negative 0.5. And u dot n at the outlet, well, it's the same argument in reverse, right? So you have now the n hat vector is going to point that way, and the u out is also going to point that way, right? So they're both aligned again, so that the magnitude isn't going to change, but the sign is going to be positive because they're pointing in the same direction. So it's going to be some, whatever the outlet velocity is, and that's going to be it. It's going to be just a positive sign. But this outlet velocity varies with position. Or at least we don't know that it doesn't. So that's going to be our next challenge. So let's write this up what we know. So we know that this thing has to be equal to 0. So we said that this, A in u dot n in ds plus over the area of the outlet, u dot n ds, that has to equal 0. And we now have some expressions for this and for this, though not completed, but we've got some things to put in there. So let's do that. So for A n, we decided that u dot n was just equal to negative 0.5 meters per second. And then we have to integrate that over the surface. And for A out, we have u dot n, well, we decided it was, that's a dot product. We decided that that was positive, but we don't know its value yet because it's u outlet. And that outlet changes, potentially that outlet velocity changes over the surface. Now, the inlet velocity doesn't change over the surface because we were told that it's a uniform inlet velocity. So that was a critical point I should have emphasized. Like this is just 0.5, and it's completely the same over the whole surface because the problem statement said you have a uniform inlet velocity. So this is literally constant over this integral. So we can pull that out, and you simply have the area of the inlet integrated across the surface. Well, that's just going to be the area of the inlet. But on the outlet side, we don't have that luxury because u outlet is not necessarily uniform. In fact, it's not uniform because we know the no slip condition applies. So we know that at the exit of the nozzle, at the very least, the fluid velocity right at the edges of the nozzle is going to be 0. So it may be faster in the middle, it may or may not be kind of uniform in the middle, but right at the edges of that nozzle, it's going to have 0 velocity. So it can't possibly be uniform. But what we can do is we can say, well, okay, but we can do an average velocity. So we're going to say that this is 0.5 times the area times the integral of the inlet area over a surface, which is just going to be the inlet area. And this is going to be some average outlet velocity. So that's not a vector symbol, that's a line indicating an average. So that's an average velocity integrated over over the outlet area. So that's it. We're going to say, all right, those have to equal 0. So that means this should be meters per second. So we have negative 0.5 meters per second times the area of the inlet plus this average, which we don't know, but which is actually what we're trying to find out, times the area of the outlet. And we can solve that for the outlet velocity. So the average outlet velocity is equal to 0.5 meters per second times the area of the inlet divided by the area of the outlet. This is a very common result when you're dealing with incompressible flows through things like nozzles. So this is worth at least thinking about. This is your inlet velocity, so your area times your area of inlet times your inlet velocity divided by your outlet area is going to give you your average outlet velocity whenever you have this kind of situation. In this case, we can go plug those numbers in because we have everything now. We know how to calculate inlet area and outlet area. So the average outlet velocity is equal to 0.5 meters per second times 0.08 over 2 squared times pi divided by 0.025 divided by 2 times squared times pi. And of course, in this case, the pi's cancel, the 2 squareds are going to cancel. So we end up with that the outlet velocity, the average outlet velocity, is the inlet velocity times the square of the ratio of the diameters. And if you do the math, that comes out to be U out average is equal to 0.5. Sorry, not 0. Well, stupid. The average is equal to 5.12 meters per second. So that's our answer, 5.12 meters per second. What is this? This is the average outlet velocity. So this illustrates both the strength and the weakness of control volume analysis. The strength is it was really simple algebra. In the end, all we had to do was do this silly algebraic equation, get the ratio of the diameters, square it, and multiply it by the inlet velocity. Great, nice result, easy to calculate. The bad news is this tells you nothing about the actual velocity at a specific level. We know it's not the true velocity. The velocity has some kind of profile. I don't know what the profile is. You don't know what the profile is. It's not all just coming out at 5.12 meters per second. It's coming out as an average of 5.12 meters per second. So it's a very useful engineering result, and we'll use it for some things. But it's also important to be aware that this kind of control volume analysis, it doesn't give you any insight into the details of the flow.